I know we're all dreaming of a day where we can take a bus like this and fly all around space. We'll start with Bishop Bubble, but in reality, rockets look more like this, with the payload or stuff on sent to space making a very small portion of the rocket. But why? Let's explain the situation. Imagine we want to send 1 kilogram of payload into orbit. How much energy do we need? Well, we can add in the potential energy required and the kinetic energy required, which gives us total energy, 3.6 times 10 to the power of 7 joules, or about 10 kilowatt hours, which would only cost about $1 per kilogram. If this was the case, the space industry would be totally revolutionized and everything would be super cheap. But we have to ask, where are we getting that energy to lift the payload? Well, we get it from fuel. But now that fuel adds to the mass. So where does it go to lift that fuel? And the fuel to lift that fuel that's lifting the payload. You can see how quickly this adds up, and this is the principle behind the rocket equation. Yep, this is rocket science. Before we dive deeper into the equation, let's look at this rocket. In the initial state, the mass of the rocket consists of the mass of the propellant, payload, and structure. But now the final mass only consists of the structure and payload, not propellant. So the mass of the rocket is constantly changing, and it's why we need a fancy equation to depict it. So how did we even get this equation in the first place? Basically, the rocket equation is derived from the conservation of linear momentum, which says force is equal to exhaust velocity times mass flow rate, and Newton's second law, force equals mass times acceleration. Since these both solve for force, we can set the equations equal to each other and simplify the terms. Now, since the mass is always changing, we need to integrate this equation. If we do that, we arrive at the final equation, the ideal rocket equation. This tells us the amount of change in velocity you can get by burning a certain amount of propellant, and it depends on the ratio between the initial mass and final mass of the rocket. So, what does this equation imply for rocket launches? If we plug in the values, we can see it takes a very high amount of fuel to carry a certain amount of payload. We can also look at past examples of rockets. The space shuttle was around 85% propellant and less than 2% payload, compared to a car, which can have only 5% fuel. This is very inefficient and limits what we are able to achieve in the space industry because of the size and money required to send anything into space. But don't lose hope yet. Many engineers are taking steps to lessen these effects. For example, stage rockets drop off extra mass once the fuel burns up. Also, in the future, rocket engineers are looking at setting up fuel stations, especially for longer missions like the Moon and Mars, to reduce the initial mass. So maybe one day you will get to see the rocket of your dreams as we push the boundaries of space exploration. Until then, we'll just have to